Yes. There'll probably be one next
Hey everybody, it's 7 o'clock. We're gonna get this show on the road. Welcome everyone to February 8th, 2024 meeting of the North Texas Archaeological Society. Got a few general announcements. First of all, welcome to our new members. We've added 9 new members since January. It's a general reminder to the room that it is time to renew your NTAS membership. You can do so online, via mail, or if you have 20 or 25 bucks with you tonight, I'm sure Gwen Durant would be happy to receive it. This is a reminder that we are providing free NTAS memberships for students via the NTAS sponsored student membership. Please see our scholarship page if you're a student. Follow the instructions, and I can almost certainly guarantee you that you will receive a free membership from NTAS. We've got a lot going on in the month of February. The 29th annual, annual is the correct word. The 29th annual East Texas Archaeological Conference will be held at the University of Texas at Tyler on Saturday, February 17th. If you attended the TAS annual meeting in Tyler 2 years ago, it is going to be in the same building. If you want some more information on that, please contact Tom Guterjohn. On Saturday, February 24th, SMU will be hosting its second open laboratory day from 9 a.m. to 5 p.m. This is going to be a recurring event, so if you can't make that date, we'll be doing it again in March, April, and May. The current focus is on artifacts collected from the 1971 and 72 TAS field schools that were held in Kirk County. If you would like more information, please contact our VP of Projects, Brian Lutford, who is in the room with us this evening. The Texas Tech School of Art is hosting Chase Earls for a traditional Caddo pottery demonstration February 22nd through 24th. I know that is in Lubbock, but if you would like to go to Lubbock, sessions are free and open to the public. It's a rare opportunity to be able to do that with Chase Earls. So if you're in the Lubbock area or you want to drive to Lubbock that weekend, I can't say anything positive about Lubbock necessarily, but I can say lots of positive things about the ability to hang out with Chase Earls and learn about traditional Caddo pottery. This is a reminder that if people are from Lubbock, I didn't think Lubbock's fine. I didn't mean
Too late.
Go Raiders. This is a reminder that an ad hoc projects committee was formed by our executive committee in December of last year. If you're interested in participating in this committee, please contact Julie Barrera. Our March 2024 guest speaker will be Lance Tomakera. Thank you, Bob Lovett, for helping us secure Lance for that presentation. This is serve as a general call for, and I have not heard if Gus has filled these spots yet or not. So I'm going to assume that they still need 4 to 5 volunteers to assist in the next round of excavations at the Nighthawk Bison Jump site in Caprock Canyon next month. They're looking for experienced volunteers to help with the excavation. Volunteers will need to be able to hike 2.2 miles round trip and climb and descend a 45-foot cliff. He has not said anything to me about whether you would be repelling or not, or if that equipment is provided. But if you are interested in volunteering for that, please contact Gus Costa for more information, or ask Charles, who I'm sure will be there. Registration is a couple of dates to put on your calendar. Registration is open for the TAS Field School, which will be in Nacogdoches again. I said it right. I'm learning. It'll be held June 8th through 15th. For more information, please visit the TAS website. The TAS annual meeting will be held in Victoria the weekend of October 25th through 27th. And this will serve as a general reminder that NTAS scholarships are available to anyone for the field school and the annual meeting. Please visit the website to apply. Before we get to our February guest speaker, our publications editor would like to have 90 to 120 seconds. She promised.
I was given that very specifically, so I did want to just put this out to all. You all know that volume 2 of the journal has come out, and we are actively seeking articles and reports for volume 3 for the 2024 volume. So I wanted to put it out for membership, make sure you all know that we are seeking those from you, from the members. We view the journal as having sort of a twofold benefit for the members. The first is that you all get to read it and have copies of it for a year before it goes to the general public. But the second benefit for you all is that it's a place for you to publish. So we just wanted to make sure that you all understand that we have it there and we want your information to go into it. If you're working on a field project, if you're working on a research project, if you have a legacy collection and you find some interesting aspect of it that you want to report on, that the Journal of the North Texas Archaeological Society is a place for you to do that. And lastly, we don't want it to be an intimidating process. If you've never published before, that's fine. If you've published many times, that's great. We still would love to have you contribute. If you are interested in sort of the details of what's required, there's less than 1 page of text about it on the website. It's not too much that we're stringent about, but you know, if you have questions about how do I get my year's publication ready, or how do I make an overview map of the project area that I'm talking about, or things like that, we're willing to help you. I don't want those kinds of things to hold you back from wanting to submit and contribute to the journal. So thank you for my 66.
Thank you, Molly and Jimmy.
One announcement from Zoom, Dr. Chris Lentz wanted everybody to know that the New Mexico Archaeological Society is holding their 2024 meeting May 3rd through 5th in Las Vegas, New Mexico, with the topic of archaeology in northeastern New Mexico and Pueblo Plains interactions, rare event for New Mexico and perhaps relevant to Texas. May 3rd is the reception, 4th papers and banquet, May 5th. Field trip. So May 3rd through the 5th in Las Vegas, New Mexico will be the New Mexico Archaeological Society 2024 meeting.
Thank you, Jimmy. Thank you, Chris Lentz. I have one more thing. We've been advertising a teaching kit day at Richland campus of Dallas College for February 10th, which is this Saturday. We are going to Dr. Sullivan is going to postpone that and reschedule it. It seems that the overlap with the brand new TAS Academy is hurting our ability to get volunteers for that. So we will reschedule that, but for this weekend, it is off. Okay, with that, please join me in welcoming our February 2024 guest speaker, Dr. That's all.
Everybody hear me? Yes. Great. Well, thanks for the invitation to come and talk. So I riffed on this is because this is a subject that I've been curious about for a very long time. Have not really done much with until the last 5 years. And it was the original second running title for this was looking at the effect of water on earth element deposits, which is kind of the ultimate goal of what I'm trying to get at. But quite honestly, if you look at what the presentation is going to be about, it's looking at the molecular composition of organic materials that comprise these types of features. So if you didn't think you were getting a good rest, now you really will. But first off, apologies to Philip Pullman. If you're familiar with his series of books, his Dark Materials, you may be aware that there are some flavorful characters. And this presentation will not have any armored bears. Best you get is my dog James. He can kind of pass for a polar bear, but no armor. No golden compasses, and this is not like the first book, which is the Book of Dust. This is the Book of Dirt. So beware. So what I'm going to talk about, earth oven facilities and features. We call them burned rock middens. And I suspect most of you are probably familiar with these features. And probably like them, hate them, both, probably a little bit of both. And this is a pretty typical example of one. This is the Gatlin site near Kerrville, which was a very well-developed burned rock midden. And these things typically consist of a lot of burned rock, burned broken rock, and black dirt. And they're pretty much created mostly by people. It might surprise some of you to find that back in 1998, Bill Martin and Jim Bruseth in an opinion piece in CRM News and Views identified burned rock middens as one of the chief problem sites in Texas archaeology. And they identified these sites as sites that we have done a lot of excavation with and really haven't made a whole lot of progress on. Now, at the time, I can kind of understand that. You read the literature back prior to the 90s, and yeah, we dug a lot of square holes and dirt that had a lot of rocks in it and kind of went, we didn't say a whole lot about them. There's been a lot that's changed since then, but and I don't know how much it's attributable to this kind of opinion piece that PhD put out, but one of the things I liked about this was it was actually a formal acknowledgement by the Texas Historical Commission that our work, as especially doing contract archaeology, contributes to a body of scientific literature. Our work is intended to be additive. We're trying to recover information about the past. And if you go through this in a kind of a rote sort of way, you tend not to recover much information, especially if you don't know the literature very well. So I kind of like the idea that they were saying, go forth and put on your thinking caps, and sharpen your pencils and try and figure it out. A lot of our colleagues then went, Jim's not going to let us take those. Too bad. I like this because it forces you to strive to think harder about what we can learn from these features and push the envelope in terms of our knowledge and technology. This was nothing new to me. I cut my teeth working with Mike Quigg, and Mike Quigg was fearless when it came to basically pushing the envelope in terms of understanding what we can learn about the past from prehistoric features. But this is kind of the mindset that permeates this research that I'm going to talk about today. So the subject, these are sometimes called anthrosols. These are things that are created by people. We call them middens, but I'm going to distinguish there are two different variants. I'm going to talk about anthropogenic sediments. This is a deposit created by people. So very simply, a burned rock midden is an anthropogenic sediment. They can be much more complex than burned rock middens. Think terraces or race fields or buildings, all sorts of different things can qualify as anthropogenic sediments. But these are places where people were the prime agency in creating them. And so the artifacts that are there are usually quite rich, and it's not a terribly challenging place sometimes to actually learn about what people did. Anthropogenic soils are kind of a different beast altogether. These are soils that have been changed by things that people have done to them, things generally they've added to them. And this can be an intentional addition or an unintentional addition. I was recently doing some contract work in Dallas and found that there are all sorts of anthrosols on the southeast side of downtown that were unintentionally modified with lead, associated with lead smelters. So there's really unpleasant ones. Most of the traditional ones are going to be, additions associated with the kind of refuse that people generated in ancient societies. The first time I had a chance to really cut my teeth and play with this, and this is where sort of my awakening sort of took hold, was during the project wheel in the southeastern part of New Mexico at the Boot Hill site, which was excavated by avocational archaeologists back in the 50s. And This is southwest of Hobbs, New Mexico, and the site is on top of a hill. And knowing there was an anthracol there, I should say, I didn't know there was an anthracol there until I got there. And it really kind of knocked my socks off to see what this site looked like. Later, after I left the field, I went and looked at Google Earth. You can see this thing from high altitude on Google Earth. This is a big black splotch on the landscape. Well, when I got there, I was like, right, what did they do? So I put in place a small research frame to try and understand this a little bit myself. So this photo on the right is the actual matrix from the Boot Hill site. And the photo on the left is the next hill to the north, outside the site. They're same geology, same topography, pretty much all controlled. The only difference is people. And quantifying what's there, there's 5 times to 15 times the organic carbon in the soil inside. And so I looked at the amount of carbon. I looked at the stable isotopic composition of the organic matter, which gives us an idea of roughly what kind of organic matter contributed to the formation of this. And what I was able to demonstrate, there's a lot more carbon in the anthracol in the site, and it's a little bit shifted towards kind of woody vegetation, C3 plants. That's it. That's all I could say. My toolkit failed me at that point. I left going, what the heck did they do here? Because I couldn't tell. Fast forward a few years, and I was doing work in tandem with the Ancient Southwest Texas project down around Langtree with Steve Black. And one of the places that we did a lot of work was this place. This is Eagle Cave. Many of you've probably been there. And Eagle Cave has been excavated multiple times. And the goal of the project, the Ancient Southwest Texas project was aimed at, was to fill in the excavations that have been done by our archaeological ancestors, who had not filled in their holes. And this is probably one of the most informative archaeological deposits that I've come across in my career. And it was being allowed to slough in and get destroyed. And so the landowner, Jack Skiles, was really hoping somebody would come in and actually fill this hole in so that it would preserve these deposits for future generations. So that was kind of the remit that we had going in. So we ended up cleaning off steps profiles and doing limited narrow excavations along this large set of excavations, along trench wall. So it was basically it was a low impact, but maximum value in terms of the kind of work we were doing. This is the profile that we ended up with from the main trench in Eagle Cave, and you'll see this later. But it was working with this that sort of stimulated my other epiphany that I'm going to talk about today. And one of the weird things that really was kind of a random walk to get to this point, but one of the things that really slapped me in the face was a story that Ken Lawrence recounted to me, which was Ken, myself, Leslie Bush, Kevin Henselka, various other people in the project have worked with master's students at Texas State University that did their master's project with the project. And so Ken was recounting helping one student look at phosphorus analysis from the UT North excavation. And the way phosphorus analysis works is you take a gram of soil, put it into a flask, add in this case, an acidic reagent, and you swirl it around, let it sit for an hour. It reacts and pulls the calcium-bound phosphorus out of your dirt, and then you pass it through a filter paper. And to get the dirt out of the way, collect the liquid. Into the liquid, you add vitamin C, ascorbic acid, and that turns that deposit blue. And how blue it is a function of how much phosphorus is present. And then you use the spectrophotometer to measure the transmittance of how much light is obscured by the blue. And that way you can quantify the amount of phosphorus. Well, Ken recounted doing this on some of the Eagle Cave deposits, and when he went to pass this through the filter paper, some of them had turned mucilaginous, slimy, if you prefer, snot-like. And at which point we were just like, what the heck? And at that point, it sort of started to dawn on me. These are deposits that are unweathered. There's no water gets in here for the most part. They're almost entirely anthropogenic. And there must be a whole world of biomolecular evidence, biomolecular artifacts, if you will, that are in these deposits that we are, up until that point, I was blissfully ignorant of. At that point, I was just like, huh, okay. And so from that point, it also became apparent that my traditional toolkit kind of failed me. Working with organic matter and soils analysis and geoarchaeology, you find out that our toolkit is a blunt force tool. We can basically say, yeah, there's organic matter. Some of our measures are really bad. Some of them are fairly precise, but at the end of it, you find out how much carbon is present. That really doesn't tell you much. So at that point, I started wondering, I was like, well, okay, how can I figure out what's in this material? What is actually comprising the organic matter that's there? What are these molecular artifacts that are present in these deposits? that are an artifact of human behavior in the distant past. Well, as I'm having this epiphany, I'm also been rummaging around the literature, and around 25 years ago or so, the geochemical community, in their quest to find ways to sequester carbon from the atmosphere and put it into some place where it doesn't get back to the atmosphere, discovered middens. And they found out that if you can put carbon charcoal into dirt, it'll stay there for thousands of years. And they had a communal geek out over this, and they just went to town on it. And there is a huge literature that has flourished in the last 25 years of geochemists going, what is charcoal? We think of it as charcoal. They've subdivided at least 5 different categories now, based on various different attributes of it. And there's just all sorts of interesting things to play with now. So I've decided to sort of crack into that literature as best I could. And so, but like I said, they first got into this when they discovered what are called Amazonian dark earths, or tierra preta. And you might have heard of this kind of revolution. It's called biochar. And this is where they sort of jumped in, and they've been looking for ways to facilitate biochar, because biochar in soils like those in the Amazon, which are extremely leached, if you add charcoal to it, it makes those soils fertile. And these soils are notoriously not very fertile, especially if you take the forest away, all their organic matter goes away. So that's where they went at it from. Well, what I found after reading through that literature is, that there are lots of new acronyms that I was unfamiliar with, that that reference different types of analyses. And so I started jumping in and trying to test out different types of analytical procedures, and we'll talk about a few of these. But the challenge on this whole thing is finding playmates, people that are willing to work with you. And that has been one of my big limitations on this approach until now. But some of these methods, thermogravimetry, carbon-13 NMR, PYGCMS, we'll talk about these in particular. Some of these are really kind of fascinating. Thermogravimetry, that thing you're looking at there, that box, is a balance and an oven. And what you do is, in this case, if you're looking at dirt, you put your dirt into this thing, and then you program the computer to raise the temperature at a rate that you ask it to. And then what it does, it records how the weight of your sample changes as the temperature gets higher. So if you think about this, if your sample has water in it, you get up to 99.99 degrees C. So you cross the threshold of 100, poof, you lose a lot of mass because water, evaporates because it turns to steam. So there are all sorts of other compounds that basically combust or disappear at different temperatures. The challenge on that is that you have to know something about your material to actually understand what something volatilizes, what it was that went away. So I thought that was cool. Then I read a paper where somebody said it had a brainwave and thought, let's run a nitrogen stream past that chamber, capture all the whatever comes off of the sample, right past a gas chromatograph, and find out what it was that was volatilized at each temperature step. I was like, okay, now you're talking about something that can actually get you where you might want to go. Never been able to get access to these. So much for that one. Surprisingly to me, the first time we actually had a chance to play this game was with Carolyn Masiello at Rice University. And her stock in trade is this device here. It's a carbon-13 nuclear magnetic resonance spectrometer. Looks like a big water heater. Costs $500,000. And works with a sample, and this is one of those little things of science that you just sometimes read about and kind of go, really? Apparently, when they first developed this thing, that they would put a sample into it. They said it's a gigantic magnet, and your sample is about the size of an eraser on a mechanical pencil. And basically, it takes your sample and it puts a little plastic thing, has fins on the side of it, so it's put a sample in, put at the very top of it, and it takes it down into the center of this giant magnet on a cushion of air. And then it gets into the center of the thing, and it shoots air past it and spins it at 2,000 RPM. And then it starts charging this giant magnet. And what they found when they first developed this was all they got was noise. However, somebody apparently trying to figure out why they were only getting noise, farting around as far as I can tell, figured out that if you put it at a specific angle, then all of a sudden you got data. They call it magic angle spinning. Science, mind you. But anyway, this thing was a fascinating device. I never thought I'd ever get near one of these things. Rice has 3 of them. And it was interesting to work with these guys, but we gave them 6 samples to play with, and it really taxed the threshold of what they were willing to do. It's a fairly labor-intensive way of playing with it. This instrument is basically the workhorse in organic geochemistry, because it allows you to study the bonds between organic molecules. Anyway, we had some experience with it, but it didn't seem to fit kind of the remit I was looking for. Then I came across the gas chromatograph and a mass spectrometer. And this is actually what I'm going to be talking about today, is all the work that follows this is basically using this setup. And I'll talk a little bit more detail about that in a few minutes. But the challenge has always been finding somebody that's willing to play this game. And so I finally looked into this, came across my colleague, Jerry Call, who's, I like to refer to him as the quintessential European citizen. He's Dutch by birth, lives in Spain, works for a German university, and he has some gas chromatographs. And Jerry has been very willing to work with me on this. And so we've done a whole series of projects now as I'm trying to feel my way and see if this is going to get me where I want to go. And I'm not sure yet, but we're making progress on it. So far, I've done 2 BLM projects with it, 1 textile project. We've done the work that I'll talk about today with Eagle Cave. And I got 1 more project coming up on this, mostly looking at earth ovens and or anthracites. Thing on the right is from Jerry's webpage, just to give you the kind of weird stuff that he gets into as well. Works on terrestrial and aquatic deposits and various aspects of organic geochemistry. So the methods that Jerry uses basically are 2. He specializes in what's referred to as pyrogenic organic matter. This is organic matter. Think of it black carbon. This is stuff that's created by fire, basically. And there are 2 preparations or 2 ways to run the gas chromatograph with this. One is PYGCMS, pyrolysis gas chromatograph. And this is basically looks at fire residues in black carbon and the kind of compounds that evolve from that. So benzene, polycyclic aromatic hydrocarbons, and benzonitrile, things like that, which you're all going, huh? Yeah, so did I. Reading Jerry's reports was quite an experience. And I'm still on the steep learning curve. He uses one other approach, which is thermally assisted hydrolysis and methylation, which is just using another reagent to actually assist in seeing polar compounds a little bit better. And it's better for looking at fatty acid profiles, specifically identifying plant and animal fats, and then or differentiating kind of sources of herbaceous type material like herbaceous versus woody vegetation on the basis of the lignin products. So a little note about Jerry's data reduction. This work creates a phenomenal amount of information. This thing on the right is 1 of 3 pages of the analysis on 1 project. And it created, in this case, 161 different pyrolysis compounds that came out of the samples that we analyzed. And he goes through and actually reduces these down to functional groups that actually are more digestible for normal, like me, hopefully. But anyway, so he tends to pull this back so that it's a little bit, it's understandable. So the kind of things that he digested into are things like polymethylene chains, carbohydrates, nitrogen compounds, monocyclic aromatic hydrocarbons, lignin, phenols, and polycyclic aromatic hydrocarbons. All these have kind of specific vectors by which they're created, things they derive from, kind of processes from which they are created. And so trying to hit into this and understand this is one of the challenges on all this. But the question I want to address is really, how are these 2 things related to each other? So, you know, this thing here is a pretty typical burned rock midden, an open air site. It's actually exposed to water all the time. And that is Eagle Cave right there. And it's a completely different beast in many ways. And what really got me going and looking at this deposits in Eagle Cave is, how do these things in Eagle Cave, which have all this organic matter, are they the same thing as this thing on the left, which has almost no organic matter, or at least none in parts you can recognize? And so that's where this research sort of kicks off. So one gets the impression these things are very different. And so the burned rock midden in the open air environment, they are anthropogenic sediments, but they're exposed to a lot of the same processes that soils are. So they get rained on, they are exposed to all sorts of other terrestrial processes. Animals live in them, defecate on them, do all sorts of things around them. So they have a lot of other things that happen there other than just human agency. And they often don't preserve, in fact, they generally don't preserve non-carbonized material. And if there's carbonized material, there's usually not a whole bunch of it. At least not in big chunks you can recognize with the unaided eye. Eagle Cave earth ovens, on the other hand, are kind of a different beast. This is an environment that is exposed to basically no water. Dew and mist are about the only things that get in there. There is a little bit of water that seeps out of the back wall, but it only really affects the deposits within about a foot of the wall, as far as I can tell from looking at things there. And these are not entirely, but pretty close, almost entirely anthropogenic sediments. And they have almost no evidence of any kind of pedogenic processes in the soil forming process. So the research I'm going to talk about has kind of a basic assumption and some basic kind of goals. The initial assumption is that these features, these middens, if you will, these earth ovens, are basically the open air site, and the kind of things that are going on in Eagle Cave are basically birds of a feather. They're the same thing created, same kind of cultural processes created them. That may not be true. We'll come back to that. And so my quest is to look at something that probably you've all passed through a sieve but really haven't thought much about, is what is that black dirt? What is it? Where did it come from? What is it made out of? How did it get there? What is it? What can we learn from it? As I can tell in the history of burn rock midden research, almost nobody's looked at this stuff. Not that I blame them, but it's just not there. So I'm looking at this from a variety of basic properties, but also then getting Jerry to look at these things in terms of pyrogenic organic matter to see what we can learn from it. And the question is, is I think the presence of water makes a huge difference in how these things get preserved. And that will be something we'll come back to. But ultimately, one of the things I want to do is I'm hoping that we'll be able to take this organic geochemistry approach and work it backwards to understand what kind of things people did there in those shelters from just the biomolecular kind of perspective. What food is there, what fuel is there, what kind of fecal material is there, that kind of thing. Okay, so I'm going to talk about two different sites. One is 41 CR 56, it's in Crane County, and this was a bird rock midden that was excavated by Montero for the Department of Transportation. And the other one is going to be at Eagle Cave, and which is a rock shelter in Eagle Nest Canyon, and it was excavated by the Texas State University Ancient Southwest Texas Project. So in terms of a map, they're about 100 miles apart. Here's CR 56, south of Crane, due south of Odessa, right north of McCamey. And it's at the very eastern edge of the Pecos River Valley. And then here is Eagle Cave down here near Langtree, west side of the Pecos River, but basically they're kind of same kind of climatic regime. Now, when I first did the 41 CR 56 work, that project was done for TxDOT, and this originally was not just looking at bird rock midden versus another bird rock midden. It was actually comparing that bird rock midden to what was looked to be a late prehistoric village site on a sand dune just south of Crane. And it had an extensive anthrosol. This is wind-blown sand. It's on top of the dune. It had a lot of organic carbon in it. Had some of these features like this one here, very nice little earth oven feature. But they also produced turquoise, troubadour black on white. And so it probably was a village. A lot of them, it was outside of the right of way, but it was pretty clear people had been there for a while. And I hadn't seen a sandy deposit like that had that much organic matter very often. So, and luckily TxDOT let us put these two things together and contrast them. So a lot of the stuff we did on this was not really comparing, well, it was comparing these two different kinds of anthrosols, if you will. So this is a photograph of the 41 CR 56 bird rock midden. It was an angular bird rock midden, so it had donut shape, it's got a central depression. So on the left side of that, you see the annulus, which has got a lot of spin bird rock over in here. It's a little weird to do. And then there's a central depression, which has a lot less rock in it over here. And the yellow dots are where I took my samples. Now, you're kind of going, what kind of crazy sampling regime is this? The logic here is this is a way that we sampled some of the deposits in Eagle Nest Canyon. And the goal of this was to cover it relatively evenly, and to then, whatever we analyze out of these samples, we can then create heat maps of to see where these things, these substances live within this cultural feature. And so that was kind of the goal of it. So for the cross section you're seeing there, here is the long section, is that part there. And then here is the short section that's in the central portion of the basin where the earth oven would have been. So that was the way we sampled it. But like I said, we did a lot of the ancient Southwest Texas like this. And I found that has a very distinct approach or distinct advantage in terms of interpretation, which you'll see as we go. So this is an example of one of the features we did in Eagle Nest Canyon. This is Skyle Shelter. You can see all the holes in that wall we've burrowed into taking out dirt for doing just this kind of analysis. Unfortunately, we haven't done this yet because we're still looking for funding to fund some of our analytical work on the Eagle Nest Canyon stuff. But this is the kind of thing we're aiming for. And so what you're going to see in these drawings is going to be a long section, which is the torus, the green part of that little bird rock, and then a little stubby bit on this side over here, which is the central depression of the bird rock midden. And so we just, whatever we generate in terms of information, we can plot that way. And you can see how these properties vary across this feature. So magnetic susceptibility is this very simple one. It's a measure of how magnetizable your dirt is. Exposing dirt to heat over a certain temperature actually enhances the magnetic susceptibility. So by all rights and all logic, I would have thought that the central depression where there was the earth oven was going to have the higher magnetic susceptibility, but no, wrong again. It's actually in the torus for some reason. And I think that has something to do with smothering the fire when you close an earth oven, which it creates a reducing environment that changes the way the magnetic minerals are created in association with heat. So right there. We looked at other things like carbon. how's carbon plot again? Red is high, blue is low. So in that very top figure, I would have thought that the central depression had the most carbon in it, but no, I'd be wrong again. Actually has less than the annulus. Carbon nitrogen ratio, however, there's a pattern there. And what the nitrogen is telling you is this is where modern vegetation. Okay. So we'll come back to that because we have other evidence to suggest that as well. Carbon 13, so in this case, let's see, red is minus 18.5 and the blue is minus 22. So it's more C3 rich in the place where the earth oven was. That reflects kind of wood for fuel, so that kind of makes sense. So a lot of these properties, if you see them in a column, you might not understand it. When you plot it spatially across a profile like that, it starts to make a little bit more sense in terms of both behavior and in terms of how these materials were moved around by people in the past. We start playing around with the pyrogenic material, and in Jerry's analysis, you start to see other kind of trends showing up. This is the products of intact plants and microbial organic matter, various different things in this. And they show kind of the same thing you saw with nitrogen. This carbon nitrogen ratio is it starts to show very nicely that there is a concentration of material across the top of here that is due to microbial organic matter and also uncarbonized plant remains. See that with carbohydrates to some extent as well. We see it with total nitrogenous compounds like this, and as well as with lignin. So these show a same pattern. They're not all concentrated at the very top, but of course these plants have roots. And so those roots penetrate down into this deposit. So you can kind of imagine that when people abandoned this feature, it was like the core of this deposit all the way through. And as it's been sitting there for the last 1,500 years, soil processes are starting to degrade what's there and permeate down into it. In the process of trying to understand how this feature related to the Embersol at the other site, Jerry did principal components analysis because there was a ridiculous amount of data to reduce and try to understand. And the pyrogenic organic matter tended to show this pattern very nicely. It shows that by the two principal components that basically pyrogenic organic matter is concentrated in the core of the annulus and in the central depression, and it's lowest across the top of the thing. And I think that must have been a big burrow or a root. I don't remember there being anything specifically there, but so you see a pattern there as well. So it's starting to make sense. This is a plot of just the results of the principal components analysis looking at the anthracite, which is the big vertical thing here, versus the burned rock midden. They overlap somewhat, but they are different. And it was kind of surprising to me that one of the weird things that came out of this was learning that the fires that were used to create the burned rock midden were lower temperature than the ones that were created, the charcoal that went into the anthracite. At one level, it kind of makes sense, the kind of things you do around the campfire and cooking, specifically maybe higher temperature than what you're doing when you're basically baking stuff. Never would have guessed that from, just looking at the dirt. So it's kind of counterintuitive, some of the stuff. Okay, Eagle Cave, different beast entirely. So this is a work that I worked up my part of this, like we've done with other masters, since this was the part of Charles Koenig's doctoral dissertation that he just completed this last year. And he looked at a section of the Eagle Cave that spanned the terminal Pleistocene up through middle Holocene. And so he asked me if I'd work up the samples from that. I was like, sure. So I worked up my part of it and had a few epiphanies in the process of doing that. Unfortunately, we didn't have a spatial sample of this. It's just a column profile. So it kind of holds you back in terms of understanding the process a little bit, but we shall see. So this is that big profile through the middle of Eagle Cave again. And the part we're going to be talking about is this here, the EOFs. EOF means Earth Oven Facility. And so in terms of when we first started interpreting this deposit, we recognized some very clear Earth Oven features, big burned rock midden, and then some other things that weren't. And so that's a simple rendition of where the Earth Oven facilities were within that profile. But the red rectangle is the section that we worked up. It's this part right here. These deposits below here are late glacial in age. That's almost all frost shattered limestone off the walls. We have a Paleo-Indian occupation in that. And there is no charcoal for the most part in that. And right at this point right here, just below that thin lens, which is called EOF1. That's about 10,500 years ago. And that is when people had the idea that you can bake things, and all of a sudden the whole trajectory of what got left in sites changed. And all of a sudden, there's charcoal everywhere and lots of burnt rock. And this is the only place I've been where it's binary like that. The hardest that we had with the Paleogene site were flat line on the ground surface. No burnt rock. It discolored the limestone, but nothing like what you see in the archaic. The bottom figure is basically the different strata that we analyzed as part of this analysis. Slightly different view of that, where the column is. It shows some of the samples for the part of the profile I appear out of place are actually in this column over here. But so I worked up my kind of standard thing. I did the particle size, I did the mineralogy, we did the carbon and the nitrogen, and then the stable isotopes for carbon and nitrogen. And one of the things that, and so basically out of all of these, I mean, this is digested out of Charles's dissertation, is he recognized that there are clearly 3 earth oven facilities in this stratum here, 594, which is the oldest, this one here, 525, and then this one up here at 385. Those other deposits he considered not to be earth oven facilities. Well, and during the primary analysis of these deposits, one of the things that kind of surprised me was when I did the particle size. And for doing particle size analysis on these, they're really hard to work with. They got really coarse material. They got a lot of I thought the charcoal was going to be the major problem because it was going to float. Turned out charcoal wasn't the problem, but I got into the middle of this profile. You can see this curve on the nitrogen isotopes over here from about there down to there. All those samples, when I went to do a hydrometer analysis, which basically is your samples in a liter of water in a cylinder that's about that tall, and you shake it up, put it on the table, start a timer, and you put a hydrometer into it, which measures the density of that solution, how much dirt's floating in the water. But you have to be able to see the meniscus at the top of the hydrometer. Those samples in the middle had upwards of 1.5 inches of floating organic matter on the top. I couldn't read the hydrometer, so I had to go get a spoon, take off all this floating organic matter, put in separate beakers and weigh and figure it out. It was kind of a shock. If you look at these deposits, you kind of can perceive it. It kind of comes down to color perception on this. These deposits here and down here are kind of brown. And that is, yeah, organic matter, mostly uncarbonized organic matter. So yeah, so just from initial point of this, it was interesting to see that there's something else going on in the middle of this that's not just earth ovens. So yeah, so Charles concluded that some of these weren't actually earth oven deposits, and but when we started playing around with the strats, it was kind of interesting to see how these things worked out, because not all the earth ovens have the same signature, which makes you kind of wonder how much variation there is in actually the molecular composition of the deposits. So those 2 in particular were the ones that had all the floating organic matter. But even this earth oven facility in the middle here, Strat 525, shares the same nitrogen anomaly. This nitrogen anomaly is coinciding very well with floating organic matter. And this probably has to do with, this is probably more grassy material, but we'll come back to that. But that earth oven in the middle doesn't match the 2 at the top and the bottom. It's somewhat of a different beast. So this is a presentation of some of Jerry's stuff. Just a little mess up at the top. This is the THMGCMS. And so the top 3 panels, those little orange bars going across are where the earth oven facilities are. So you kind of very quickly get an idea. So these top 3 panels are all reflecting various aspects of charred material. And so you can see it's high up here, not much in here, and it's high at the lowest one, but there's not much in that one. They have the same pattern for these very different compounds of char. The bottom panels are reflecting different things. So the bottom left one is looking at protein-rich organic matter sources, and they're really high, not so much in the earth ovens, but more in this kind of area where there's a lot of floating organic matter. The middle one, triterpenoids, is kind of a weird one. That's actually secondary degraded bile acids. Between the material that's there, which has been shown from this to be lignin, I mean, gluten rich, which is coming from basically grass blades and things like that. This is probably dung. So it's basically, it's a lot of, it's digested organic matter, it's kind of small bits, and it's got bile acids in it. So chances are a lot of that is probably herbivore dung of some sort. The very far right one are the methoxybenzenes, which there are 2 different parts of these, which he divided. That one of these is a tag for basically lignin-derived herbaceous organic matter. That's the red line, this line here. which shows very nicely in the area where we have all the floating organic matter. The other one is basically a tag for charred organic matter. And it also, again, it works pretty well for the upper part, the upper earth oven, and for the lower earth oven, but really doesn't register worth a flip in that middle one. So how do these two middens compare? Eagle Cave has abundant carbon. It has a high molecular density, diversity, I should say. So Jerry and his partner just had their first child. I was hoping to get more details on this, but he's on paternity leave at the moment. So we didn't get there, but he referred to Eagle Cave having a high molecular diversity. And so there were 113 pyrolysis products from the CR56 midden. So high probably is something around 200 to 300 different pyrolysis products that were coming out of Eagle Cave. It has a very small pool of microbial organic matter. And so in his conclusion was that there's got a lot more potential here to understand the organic sources that went into this than what we got out of the bird recommended 41 CR56. There, although it's black, that midden has very little carbon by comparison. It has a low molecular density, and it has a mix of prehistoric primary stuff, but a lot of organic matter is created by mostly microbial activity. So how do they differ? I've always wondered about this myself since working in these two places. This plot on the left is plotting carbon isotopic composition on the x-axis and the organic carbon percent on the y-axis. All the squares are from Eagle Cave. And so the red ones are the earth oven facilities, the green ones are the other deposits. The orange dots down here are the 41 CR56. So they're struggling to get up over 5% organic matter. Eagle Cave is running upwards close to 40% at the top. So it's a huge difference. Just for fun, I threw in some samples from Sales Adobe, which is an alluvial site that's in the canyon. Just gives you an idea, how much carbon do we find in our normal kind of alluvial sites? Usually less than 1%. And so you kind of get to see kind of how different is the Eagle Cave stuff. Really tremendously different. Right side plot is just a box and whisker plot of showing kind of the same thing. How much organic carbon is present. Sales hardly registers at all. So the first takeaway is not all these earth oven deposits have the same signatures molecularly speaking. And this was basically independent of Charles reaching this conclusion based on the artifacts and the faunal data. Charles didn't have benefit of the macrobotanical material, so we're really looking forward to being able to compare the macrobotanical story that's here from these same deposits with this kind of approach with what Charles saw in his stuff. But the molecular evidence from the gas chromatography is actually showing us a different story they don't normally get to see. CR56 is a whole different world. When I first asked Jerry, how would you compare these two? He was right, they don't compare. They're just so different from each other. They have attributes of commonality, but for the most part, most organic matter has been digested by microbes. So it's very difficult to understand what happened there. So moving forward with this research, we have a number of avenues we're trying to aim at. Like I said, we have two middens like this in Eagle Nest Canyon. We like to sample and run, just like we did for the CR56 midden, Eagle Cave and Skyle Shelter. And we're looking for funding for that right now. But beyond that, the challenge on this is we're having to build a middle range frame to understand and interpret these data. So as part of his doctoral dissertation, Charles Koenig did some experimental earth ovens. We know exactly what went into them. We know exactly what came out of them. And so we have samples from both the earthen matrix that came out of his earth oven experiments, but we also have residues on bird rocks that we're going to look at and see if we can actually backwards engineer, looking at those residues, can we figure out what was in that? In addition to that, we're looking at modern plants. And so he's already looked at Lechugia and Sotol, from which he looked at them uncharred and commented in the uncharred state that they actually have relatively the same molecular fingerprints. And so he's hopeful that we can actually go at this from kind of being able to identify discrete patterns of compounds that come from discrete plants. However, we need a lot wider range of stuff. So a few years ago, Leslie Bush gave me a bunch of materials to compare for sections. I'm also going to be using that with Jerry to actually push this work forward as well. The other thing we have to do is we have to then chart these materials to look at what they're like in the raw state and what they look like compositionally in the charred state. But that's going on right now. And as always, this is not work that I did myself. This is the effort of a lot of different people. So a lot of people did a lot of the effort, what you saw in this was actually Jerry Call's work. But in addition to that, Charles Koenig has been a willing participant to play with this kind of stuff. as has Kim Lawrence and Steve Black. Aaron Norman, Miles Miller, Tim Graves, and Jim Abbott all had a hand in doing some of the contract work in this. But most of this work has been done in the context of CRM. The only parts of this have been not the Eagle Cave work for the most part, and that I've funded myself so far. But this would not have happened without the institutions, TxDOT Environmental Affairs Division, the Carlsbad Office of the BLM, and two companies, Amatera and Versar, who've also helped fund this. So I'm gonna stop there. That way you don't fall into sleep. Thanks. Anybody have any questions? Yeah.
Question, paleo climatology, would any the source of fuel over that period, how drastically did that change? Did that make any difference? I mean, some stuff burns hotter, burns longer. I mean, would that be any kind of an effect that you're looking at, or?
Possibly, yeah. I mean, that's an excellent question. We don't really know at this stage. We haven't seen any of the macromechanical work for these deposits yet. So I can't really comment from an informed perspective on that. But yeah, composites, yeah, I mean, I think that would make some sense. But I'm also curious how much of the fuel that they're using for these features are actually derived from flotsam from the Rio Grande. Because you're right at the Rio Grande and it does backflow the canyon, and that will create a lot of readily available fuel for a long period of time. So fuel may not have been their problem. But I don't, going back to the molecular end of it, we're just at the inception of this. We're trying to work out what we can identify. I'm hoping that when we actually can marry up all of our data sets and get in the macromechanical work, that we actually will start to be able to see some patterns that are showing up between the molecular geochemistry versus the macromechanical assemblage and also the archaeological assemblage.
Any other questions in the room? Skipper?
Yeah.
The difference you talked about there between the Crane County side and Eagle Cave, was that a difference because of the controlled climate versus the open climate, or was it a difference because of a completely different type of forging and everything?
Excellent question. I'm not sure I can answer that entirely. I'd say for one, originally when we first worked this out in doing this part of the ancient Southwest Texas project, the original idea was to sample Eagle Cave, which is completely dry, Skylift Shelter, which is the wettest of the rock shelters in the canyon. So those deposits are not preserved at the same degree as Eagle Cave. And then go and find an open air bird rock midden somewhere nearby. And we've actually sampled one that was not very far away, called Tractor Terrace. So that was our original frame, was to kind of look at, completely wet to completely dry and some sort of metal in the middle. And, the simplistic assumption of these are actually the same basic behaviors is undoubtedly just that, a simplistic assumption. But the challenge is, how can you demonstrate that? So in this case, this was more opportunistic on my part. Ever since we started sampling in Eagle Cave, I've been itching for a chance to kind of tuck into this and actually see what kind of diversity and variations there are. And Charles's dissertation gave me the opportunity, gave me the kick in the butt to go do that. Because we've mostly been looking to go and do. Let's see. So I did about 20 samples for the Eagle Cave stuff, but we're talking about 100 samples for looking at one of these larger midden profiles. And journey prices are very reasonable, but that's still a sizable chunk of change. And we haven't yet secured funding for some of our post-tax analysis yet. So, but I'm waiting for that, because I think that'll be a very fascinating thing to play with.
Any other questions in the room? We have some
Hey,
questions.
Charles, this is Doug. You mentioned the herbivore concentrations in Eagle Cave. What was that source of that? Was that brought in by people for fuel? And is it just deteriorated dung, or is it burned dung that's in the deposits?
Good question. We've been waiting for samples of various late Pleistocene critter dung from Jim Mead, which have not arrived yet. So hopefully we'll get some closure on that. We've looked at one coprolite, human coprolite, but just the idea that there actually are going to be things like copper stanols, which are bile acid derivatives that are going to be present in the shelter, sure where the human material is, but yeah, this recognition that this was all fiber and it was probably done, just kind of hit everybody kind of by surprise. Yeah, once you know it's there, it's very obvious. But no, we don't know which one it is, but we're hopeful that we might be able to distinguish different animal from the kind of people biomarkers that are present, but that's yet to be determined.
Any more disembodied voices? Are there any further questions?
No questions in Zoom chat at this time. Any questions on Zoom from anybody else?
They're all asleep.
Any other questions in the room? Okay, well, wonderful.
Great presentation.
And for those in the room, I forgot to thank you, everybody, and Zoom. We will see you later. For those in the room, I forgot to mention